Hi friends, welcome back. We are into the fourth module where we are looking at the memory management. Now the thing we need to look at is what memory is and how it affects our performance, how the operating system has to work with the memory, how the memory should be managed. All that is what the issues we have to address in this memory management. So to begin with, what memory is, let's start looking at that. So memory, as we know that there are mainly two types of memory. One is the primary memory, other is the secondary memory. The primary memory is the one which is on the motherboard, and the secondary memory is one which is of large size but is very slow. It may be magnetic tape, it may be optical memory, it may be a hard disk, magnetic disks and all that. That's a secondary memory. We are not talking about secondary memory here. We are talking about the main memory. Main memory is a semiconductor memory, which is fastest to access, to read, to write. So the speed of the working with semiconductor memory is the fastest one as of compared to the primary and secondary. And the commonly used semiconductor memory is what we call RAM, that is random access memory, where any location of the memory can be accessed. There is no need to go one by one. There is no need to go in sequence like we do in magnetic tape. So if we want to go at the 10th step, then we have to keep shifting the tape 9 steps and then you will get the 10th step. But whereas in the random access memory, the access is random. That means any location in the memory can be accessed in one unit time. So that's the advantage of random access memory. There are many types of random access memories. In this example, we are showing a motherboard where various components are shown here, and one of the components is RAM. In this case, we are showing here a DRAM, that is a dynamic RAM. So that's talking about the memory slots here. And there is another semiconductor memory. We have ROM. So this ROM is a permanent memory. Is write once, read many times, but still it is a semiconductor memory, and this is used for storing the BIOS, that is the basic input output system that we had seen in the process management in the beginning. Okay, that's random access memory, and this random access memory contains the operating system as well as the processes. So there's a random access memory of particular size, and in that some part of the memory is occupied by the operating system and other part of the memory is available for the processes to occupy. Yeah, this schematic shows that there is one random access memory, and in the beginning there is operating system loaded here, and then we have 3 processes loaded here, and this number shows the locations of the memory. That means the process 1, if I say this as process 1, it starts from this location and goes up to this location. Process 2 starts from this location, goes up to this location. Process 3 starts from this location and goes up to this location from here till here. And there is nothing stored here. That means that memory is currently free. We can add any other process onto that. And usually the operating system will be stored from the first location, that is the location 0 onwards. So that's how the memory is organized. That's how the main memory, primary memory is organized usually. Then how do we address them? So as far as the programs are concerned, the major problems we face in the programming with respect to the positioning of the process. So a process can be located here, a process can be located here, process can be located here, which means that the first location of each process is different. So that is possible. So in advance we don't know where exactly the process can be loaded our one particular process. Exactly where it can be loaded, we don't know. It can be this one, it can be this one, or it can be the third one, whichever is possible. We are not sure. Therefore, the question comes is how to address them. So addressing is an issue when we want to, as long as we are executing the instructions one after other, we don't have any problem. If we are talking about this process, we begin with this location and start reading the instruction from that location and then execute, then go to next location, next location, next location, next location, and so on. So that is not a problem at all. But the problem arises when we want to change our location, like we want to jump for some reason. So on some condition we want to shift either up or down depending on the logic we are working on. At that time the problem comes is shift where. If you are talking of this process, then it is talking about these locations. If you are talking of this process, then it is talking about these locations, and so on. So there is a problem of addressing. So there are basically two addressing modes. So to make sure that your process is located at the right place. So we have two types of addressing modes. One we call absolute addressing, where the instruction directly specifies where to go. So if you are talking about a location here, then we just tell that you go to this particular location represented by this type of number. So exact address is mentioned here to jump, and the example could be jump to this location. Yeah, that is what an absolute addressing is, but there is another way of doing it, is relative addressing. And here it just tells about the offset, how many steps to move forward or how many steps to move backward compared to where you are. So you can say that jump 10 steps ahead, or you can say that jump 5 steps behind. So ahead and behind you can talk with respect to plus or minus signs, and then say jump plus 10 means jump 10 steps ahead, and jump minus 5 means jump 5 locations backward, and so on. So the advantage of working with absolute addressing is you don't have to worry anything, you just jump there. You don't have to do any arithmetic for that, you just have to jump whatever location is said. But the problem is if that process is here, then it may be this location, but instead of having that process at this location, if it is in this location, then this address no more holds good, because this address is somewhere in this region, then it jumps into some other place. So definitely it is going to create problems if we start using the absolute addressing. Then the best way of doing is relative addressing. So whether you are in this region or in this region or in this region, doesn't matter. Wherever you are, you just tell go 5 steps ahead or 10 steps behind, or 10 steps ahead, 5 steps behind. That way if you can keep telling, then it doesn't matter where the current process is situated in the memory, it just do the correct moves, and hence there won't be any malfunctioning, there won't be any problems in making the jumps and all that. Okay, now looking at the basic hardware, what we are trying to do is, if you are talking about this particular process, then this particular process we have to work with. One is about the addressing, and other thing is, while we are making jumps and all that, we must ensure that you are within that boundaries. So there is an upper limit and there is a lower limit where your process can be in the memory. So this is your lower limit and this is our upper limit. So our process lies between these two limits. So we have to ensure whenever we are working that it is within that limit. So instead of working on absolute sense, we can start working in the relative sense, that the first line here is the first location, second line is the second one, third line is here, third one, and so on. So that way we can talk indexing, and then whether it is here or here, it doesn't matter. If we say index is equal to 4, then it is the fourth line we are talking here, it is the fourth line we are talking here, it is the fourth line we are talking here. So wherever it may be, we are talking about the fourth line because we said that index is 4. Now how do we exactly know where it is? So for that we use the starting address, which we call the base address. So in this case, this process lies between 30040 to 420940. These two locations, our whole process lies. Therefore, this is our beginning address. So we call this a base, and then we see how long is this. So you subtract this from this, then we get this 120900, and that is the length of this block. So the size of the memory allocated for this process is so many locations. So this is where it starts, and that is the number of locations allotted for this process. If we have these two things, then we can start working in the relative sense instead of talking in absolute sense. And how that is done, so let's check that. And here the CPU always talks in relative sense, it doesn't talk in absolute sense. Therefore it says go to the fourth location. It says go to the fourth location, then we have base address. So is it above that base? If yes, go in. So we are talking about some location, then that location is above the base. If yes, we are talking about that process, and then verify that base plus limit, that is talking about this plus this, is 420940, if is within that. So if you are going to access any location within these two limits, then it will be above the baseline and below this line, then access the memory. If you are talking something which is below this baseline, which means that you are talking about some other process, definitely it is going to disturb. One process is trying to access another process which is not allowed. Therefore trap to the operating system in saying that trying to access the location which is beyond our limits. So one says if you are talking below the base, then you may be talking about this process, therefore you should not be allowed to. If it is above this, yes, it may be. Then make sure that it doesn't go beyond this line. If it goes beyond this line, then you are talking about the next process. So make sure that it is not in the previous process. In the same way, it is not addressing the next process. So it is yes means it is above this, and here yes means it is below this, and both yes means it is between these two endpoints. That is the process. That is the address block allocated for this particular process. Only then you allow the memory to be accessed. So that is the logic used for accessing, and here we are working with a absolute address. So we give the absolute address and then work on whether it is below base, no. If it is below base, yes, then don't allow. If it is above base, yes, then look for is it below that next boundary line. If yes, allow it. If no, then just say there is a problem.